Put your hand on the table. Go on. Just lay it flat. Feel that? Feel the warmth where your palm meets the wood? Your hand is warm, about 98.6 degrees Fahrenheit. That warmth is energy, real, measurable, physical energy. And I want to ask you the dumbest possible question about it. Where does it go? Not someday, not philosophically, I mean physically. When you die, when your body stops, when that warmth leaves your hand and your skin goes cold, where does the energy go? Does it vanish? Does it float away into some metaphysical fog? Does the universe just lose something when you stop breathing? Because here is what we know right at the start, before we get into any of the fancy business. We know with about as much certainty as we know anything in physics that energy cannot be created or destroyed. That is the first law of thermodynamics. It is one of the most tested, most reliable, most unforgiving statements human beings have ever made about nature. Energy is conserved. Always. Everywhere. No exceptions have ever been found. Not in any experiment. Not in any corner of the cosmos. Not ever. So if that is true, and your body is full of energy right now, and one day your body will stop, then the energy has to go somewhere. Every single bit of it. And figuring out exactly where it goes and how it gets there and what form it takes along the way turns out to teach you more about what you are, physically, than almost any other question I can think of. All right, let us start with just the warmth. Forget everything else about your body for a moment. Forget your thoughts, forget your muscles, forget your bones. Just think about the fact that you are warm. Why are you warm? Because inside every one of your cells, right now, little chemical reactions are happening. Molecules are being broken apart and reassembled, and each time that happens, a little bit of energy is released as heat. You have got trillions of cells doing this simultaneously, all day, all night, even while you sleep. Your body is like a furnace that never quite shuts off. Awake, asleep, thinking, not thinking, the heat keeps coming, until it does not. And what is heat actually? What is it physically? This is important. Heat is motion. That is all it is. The molecules in your hand are jiggling and vibrating and bumping into each other, and the faster they jiggle, the warmer you feel. Temperature is just our way of measuring how much random molecular motion is happening in a substance. When I say your hand is 98.6 degrees Fahrenheit, what I'm really saying is that the molecules in your hand are vibrating at a certain average speed. Each one is doing its own thing, some faster, some slower, but on average they are moving at a speed that corresponds to what we call body temperature. You can feel this, by the way. If you press your hand against a cold window in winter, the glass feels cold not because coldness is flowing into you, but because heat is flowing out. The fast jiggling molecules in your warm hand bump into the slow jiggling molecules in the cold glass, and some of that kinetic energy transfers from your molecules to the glass molecules. Your hand loses energy, the glass gains it, you feel cold. The glass, if it could feel, would feel a tiny bit warmer. So when you die, what happens to all that molecular vibration? Well, it does not stop instantly. This is something people do not always think about. Your hand does not go cold the moment your heart stops. It takes hours. And during those hours, the heat in your body is doing exactly what heat always does. It is flowing from where it is warm to where it is cooler. Your body radiates infrared light. Every warm object does this. Right now you are glowing in infrared. You cannot see it with your eyes, but a thermal camera can. That infrared radiation carries energy away from your body and into the surroundings. Your body also conducts heat into whatever surface it is resting on, a bed, a floor, the ground, and the air touching your skin picks up some of that warmth through convection. The warmed air rises and mixes with cooler air, carrying your thermal energy outward, dispersing it into the room, into the building, into the atmosphere. And where does that warmed air end up? It rises, it mixes, it spreads. Your body heat, the very same heat that kept you alive for decades, is now warming the room you are in by some absolutely tiny fraction of a degree, maybe 1,000th of a degree, maybe less, but it is there. And eventually some of that thermal energy radiates out past the atmosphere, out past the moon, out as infrared photons traveling at 186,000 miles per second into the void between the stars. A photon that was born from the jiggling of a molecule in your left hand, carrying a tiny quantum of the energy that once kept you warm, sailing through interstellar space forever. That is not poetry. That is physics. So that is just the heat, just the warmth in your hand. And already it has not vanished. It has spread out, changed form, traveled. But it is still there, still energy, still accounted for in the great ledger of the universe. But the heat was only the smallest fraction of the energy your body contained. Let me add another layer. Right now, your body is storing energy in chemical form, enormous amounts of it compared to the thermal energy. You ate food today, presumably. Maybe some toast, maybe some rice, maybe an egg. Whatever it was, your digestive system broke it down into smaller molecules, amino acids, fatty acids, simple sugars, and your cells took those pieces and reassembled them into molecules they could use. The most important molecule for energy purposes is one called adenosine triphosphate. That is a mouthful, so biologists just call it ATP. I will call it the energy molecule because that is what it does. It is the battery that powers almost everything in your cells. When a muscle needs to contract, it cracks open an energy molecule and uses the energy released by breaking one of its chemical bonds. When a nerve needs to fire a signal, same thing. When your cells need to build a new protein or copy a strand of DNA or pump ions across a membrane, they crack open an energy molecule. And here is the surprising part. You have got, at any given moment, only about 50 grams of this stuff in your whole body. 50 grams. That is less than the weight of a candy bar. But you use it so fast that your body recycles it constantly. You make and break down roughly your own body weight in energy molecules every single day. If you weigh 70 kilograms, you are churning through something like 70 kilograms of ATP in 24 hours, but you never have more than 50 grams of it on hand at any moment. The turnover rate is astonishing. It is like having a bank account where you deposit and withdraw your entire life savings every few minutes. And what does your body spend all this energy on? Let us be specific because the details matter. Start with your brain. Right now, your brain is consuming roughly 20% of all the energy your body produces. 20%. Your brain weighs about 2% of your body mass, but it demands a fifth of your total energy supply. That is an extravagantly greedy organ. And what is it doing with all that energy? Running electrical signals. Your neurons fire by moving charged ions, sodium, potassium, calcium, back and forth across their membranes through tiny protein channels. Every thought you have, every sensation you feel, every word you understand is a cascade of ions flowing through these channels, powered by energy molecules. Your thoughts are electrochemistry. They are energy being converted from chemical form to electrical form and back again over and over, billions of times per second. When you die, those electrical signals stop. The ions settle into equilibrium across the membranes. The voltage differences that your neurons worked so hard to maintain simply dissipate. And the energy that was holding those gradients in place, the energy that was, in a sense, the physical substrate of your thoughts, where does it go? It becomes heat. The ions that were being pumped against their natural tendency now flow freely, and the potential energy that was stored in those gradients is released as a minuscule amount of thermal energy. Your last thought, whatever it was, ends as warmth, a few millionths of a degree in the fluid around your brain cells. That might sound deflating if you think about it one way, but think about it differently. The energy that powered your most profound idea and the energy that warms a cup of water are the same kind of energy. There is no special category for thought energy. There is no separate ledger for the energy of consciousness versus the energy of a burning log. Energy is energy. The universe does not grade it by importance. It all counts the same. Your muscles are another enormous energy sink. Even sitting still, they consume energy to maintain tone, to keep you upright against gravity, to keep your diaphragm contracting so you breathe. When you walk across a room, chemical energy in your muscle cells becomes kinetic energy, the energy of motion, along with a tremendous amount of waste heat. You are, I am sorry to say, a terribly inefficient machine. About 75% of the energy your muscles consume is lost as heat. Only a quarter becomes useful mechanical work. You are roughly as efficient as a steam locomotive. Every step you take warms the air around you a little bit more. Your heart, over the course of your life, performs a remarkable amount of work. It beats about 100,000 times per day, pushing roughly 2,000 gallons of blood through your vessels. Over 70 years, that adds up to something like 2.5 billion heartbeats, each one powered by energy molecules, each one converting chemical potential energy into the kinetic energy of flowing blood. When the heart stops, that steady expenditure ceases. The blood settles under gravity. The kinetic energy of its flow is absorbed by friction against the walls of your vessels, transformed into, you guessed it, heat. Every form of energy your living body uses, electrical signals in the brain, mechanical work in the muscles, chemical synthesis in your cells, osmotic pumping in your kidneys, all of it eventually ends up as heat. You are, thermodynamically speaking, a machine that converts food into warmth. Everything else you do, thinking, moving, growing, healing, those are side effects of the heat production if you want to be cynical about it. Or more accurately, the heat is the unavoidable tax on all those processes. Either way, the energy goes from chemical bonds to useful work to heat, and the heat goes into the environment. So where does the energy in those molecules come from? From the food you ate. And where does the energy in the food come from? Follow it back. Say you had a piece of bread. The wheat plant that made the grain in that bread grew in a field somewhere. It absorbed sunlight. And this is where the story gets beautiful, because the physics connects you to a star. Inside the cells of that wheat plant, there is a process called photosynthesis. You learned about it in school probably, but I want to tell you what it actually does in terms of energy. The plant takes carbon dioxide from the air and water from the soil, two simple, low-energy molecules, and using the energy of sunlight, it forces them together into glucose. Sugar, a high-energy molecule. The plant has taken energy from light and locked it into chemical bonds. Photosynthesis is an energy storage device. Sunlight goes in, sugar comes out. So when you eat the bread, you are eating stored sunlight. I want you to understand, this is not a metaphor. It is not a poetic way of speaking. It is a literal, physical description of the energy transaction. The energy in your muscles, the energy that lets you think and blink and breathe and pick up a cup of coffee, that energy traveled 93 million miles from a thermonuclear furnace, crossed the vacuum of space in about 8 minutes as a photon, hit a leaf in a field in Kansas or somewhere, got captured by a chlorophyll molecule, was used to forge a sugar molecule, ended up in a grain of wheat, was milled into flour, baked into bread, eaten by you, broken down in your gut, rebuilt into an energy molecule in your cells, and is now being used to power the neurons that are following what I am saying. That is the chain. Your body is running on starlight. And this raises a wonderful question that we should not skip over. Where does the sun get its energy? The sun is fusing hydrogen nuclei together in its core, slamming protons into each other at temperatures of about 15 million degrees. And when 4 hydrogen nuclei fuse into one helium nucleus, the resulting helium is slightly lighter than the 4 hydrogens it was made from. A tiny bit of mass has disappeared. And that missing mass has been converted into energy according to Einstein's famous relation. The sun is converting about 4 million tons of its own mass into energy every second. 4 million tons every second. And it has been doing this for about 4.6 billion years, and it will keep doing it for another 5 billion or so. So the sunlight that your wheat plant captured was itself the product of nuclear fusion, which was itself the product of mass being converted to energy. The chain goes nuclear mass to fusion energy, to light, to chemical bonds in a plant, to chemical bonds in your body, to the kinetic energy in your muscles, to the heat that keeps you warm. Every link in that chain conserves energy. Nothing is lost at any step. You can follow it forward. You can follow it backward. The accounting always works. When you die, all that stored chemical energy, the sugars, the fats, the proteins, the energy molecules, all of it is still there in your body. Your body does not suddenly lose its chemical energy the moment your heart stops. The molecules are still intact. The bonds are still holding. The energy is still locked inside, sitting in your tissues like food in a pantry after the cook has gone home. So what happens to it? Here is where biology takes over from physics for a moment, and then physics takes it right back. Your body, once it stops maintaining itself, becomes food. I know that sounds blunt, but it is exactly what happens, and there is a deep lesson in it. The bacteria that were already living in your gut, trillions of them, do not know you have died. They just know that the immune system which was keeping them in check has stopped working. The borders are undefended, and so they begin to eat. They break down your tissues the same way you broke down that piece of bread. They crack open chemical bonds in your proteins and fats and carbohydrates, and they extract the energy for themselves. This is decomposition. And I want to be very clear about what decomposition actually is, because there is nothing mystical about it. Decomposition is chemistry. It is oxidation, reduction, hydrolysis, fermentation. It is the same kind of chemistry that happened in your stomach when you digested your lunch. Bacteria and fungi are doing to your body exactly what you spent your whole life doing to plants and animals. They are harvesting stored chemical energy from organic molecules. And just like when you metabolized food, this process releases heat. A decomposing body is warm, not warm because it is alive, warm because chemical reactions are occurring, bonds are breaking, and energy is being released as a byproduct. Some of that energy goes into fueling the microorganisms. Some of it escapes as thermal energy into the soil or the air. Some of it ends up in the bodies of insects and worms and beetles and everything else that arrives to participate in this great chemical recycling. Consider the nitrogen in your muscles. When you were alive, that nitrogen was locked into amino acids, the building blocks of your proteins. As bacteria decompose those proteins, the nitrogen is released, first as ammonia, then converted by other bacteria into nitrites and nitrates. Those nitrates dissolve in the soil water. A plant absorbs them through its roots. The plant uses that nitrogen to build its own proteins. An animal eats the plant. The nitrogen that was in your bicep is now in the leg muscle of a rabbit, helping it run through a field. The energy associated with those chemical bonds has been transferred, transformed, but not diminished. If you are buried, this process plays out over months and years. Your body's molecules gradually enter the soil ecosystem. Carbon, nitrogen, phosphorus, sulfur, calcium. These are nutrients, and they are valuable. The soil around a buried body becomes richer. Trees planted near old graveyards often grow remarkably well, and there is nothing mysterious about that. They are running on the chemical energy that was once in human bodies. If you are cremated, the process is faster and more dramatic, but the physics is identical in principle. Your body is exposed to extreme temperatures, roughly 1400 to 1800 degrees Fahrenheit, and the organic molecules in your tissues are oxidized rapidly. This is combustion. The carbon in your body combines with oxygen to form carbon dioxide. The hydrogen combines with oxygen to form water. And the energy that was stored in those chemical bonds is released as heat and light. The flame of the cremation furnace is, in a very real sense, your body's stored chemical energy being released all at once. It is the same energy that the sun put into a wheat plant, that the wheat plant put into a grain, that you put into your muscles and bones over a lifetime of eating. Released in an afternoon, that carbon dioxide drifts up into the atmosphere. It might be absorbed by a tree next spring. That tree might grow a fruit. Someone might eat that fruit. And then the carbon atoms that were once part of your body are now part of someone else's body, carrying energy along the same chain that has been running since the first plants captured the first photons of sunlight. Billions of years ago. Nothing disappears. The atoms circulate. The energy moves. The books balance. But I've been talking mostly about chemical energy, and your body has more than that. Let me go deeper. Your body contains roughly 7 billion atoms. Let me say that more carefully. 7 times 10 to the power of 27. Mostly hydrogen, oxygen, carbon, and nitrogen, with some calcium and phosphorus, and traces of dozens of other elements. And each of those atoms has energy inside it that I have not yet discussed. Not the chemical bond energy that holds atoms together in molecules. The energy inside the atom itself. Every atom has a nucleus, and that nucleus is held together by the strong nuclear force. Protons and neutrons packed so tightly that it takes extraordinary conditions to pull them apart. And there is energy associated with that binding. This is the energy that gets released in nuclear reactions, in fission and fusion. It is the energy that powers the sun, as I was just telling you. It is the energy that comes out in a nuclear explosion. In an ordinary death, nothing happens to this nuclear energy. The nuclei of your atoms do not split. They do not fuse. They do not rearrange. They just sit there, as stable as they have been for billions of years. The carbon atoms in your body were forged inside a dying star that exploded before the Earth existed. Those atoms have survived the formation of the solar system, the accretion of the Earth from a disk of gas and dust, billions of years of geology, oceans forming and continents drifting, the rise and fall of species. And those same carbon atoms will remain carbon atoms long after you and I are both gone. The nuclear energy stored in them will not change one bit. It will continue to exist, stored in the nuclei, untouched, like money in a vault that nobody has the key to. So your body carries around an enormous reservoir of nuclear energy that it never uses. Your biology runs on chemistry, not nuclear physics. The nuclear energy is just along for the ride. It was there before you were born. It will be there after you die. It does not care about either event. But there is yet another kind of energy in your body. And this one is going to make you pause. Mass. Your body has mass. You step on a scale, you get a number. 70 kilograms, say, or 154 pounds. And in 1905, a young patent clerk in Switzerland named Albert Einstein published a paper showing that mass and energy are the same thing. Not analogous, not metaphorically similar. The same thing. The energy content of a piece of matter is its mass multiplied by the speed of light squared. E equals mc squared. The speed of light is enormous, 186,000 miles per second, roughly 300 million meters per second. When you square that number, you get something like 9 times 10 to the 16. That is 90 quadrillion if you prefer English, which means that even a tiny amount of mass contains a staggering amount of energy. How much energy is in a human body purely from its mass? Take your 70 kilograms and multiply by the speed of light squared. You get roughly 6.3 times 10 to the 18 joules. That number is meaningless in everyday terms, so let me translate. It is roughly equivalent to the energy released by 30 large hydrogen bombs. One human body, not burning it, not decomposing it, converting the mass itself into pure energy. You are walking around every day with the energy content of a major nuclear arsenal stored in the simple fact that you have mass. But nobody unlocks it. You cannot unlock it, not under any normal conditions. Mass energy is bound up in the fundamental particles that make up your atoms, and converting mass to energy requires either nuclear reactions, like what happens in the sun, or matter-antimatter annihilation, which emphatically does not happen to you when you go to sleep at night. So that energy stays exactly where it is. When you die, your body still has the same mass it had the moment before. The scale reads the same number. Over time, as decomposition redistributes your mass into gases, liquids, soil, bacteria, insects, and plants, the total mass of all those products, if you could painstakingly gather every last molecule and weigh them together, would be exactly the same as the mass of the original body, and therefore the total mass energy is the same. Nothing vanishes. Let me add all of this up because the picture should be clear now, and I want to make sure you see it completely. When you were alive, your body had thermal energy, chemical energy, nuclear energy, and mass energy. That is roughly the complete energy budget of a human being. Your thermal energy dissipates into the environment as heat after you die. It warms the air and the surfaces around you. It radiates as infrared light. Eventually, it makes its way into space. It does not disappear. It spreads. Your chemical energy is released over time through decomposition or combustion. Bacteria metabolize your tissues. Plants absorb your nutrients. Insects carry off fragments. If you are cremated, the energy comes out as heat and light in a matter of hours. In every single case, the total energy before and after is the same. You can audit the accounts. The ledger balances. Your nuclear energy stays locked in your atoms, which persist unchanged through it all. Carbon stays carbon. Oxygen stays oxygen. The atoms get incorporated into soil, into water, into other living things. But the nuclear binding energy in each atom is untouched. Your mass energy stays with your mass, which gets redistributed but never destroyed. Every gram of you ends up as a gram of something else. Nothing is created. Nothing is destroyed. Everything is transformed. The first law holds. It always holds. And I should say something about that, about how we know the first law holds, because it is not obvious. It took humanity a very long time to figure this out, and the story of how we got there tells you something about how tricky energy is as a concept. For most of human history, people thought fire consumed things. You burn a log, the log disappears, and you are left with a little pile of ash that weighs almost nothing. It sure looks like something was destroyed. Mass was lost. Energy appeared from nowhere, as heat and light. The idea that everything was conserved would have seemed absurd to someone watching a campfire in the Middle Ages. It was not until careful experiments in the 18th and 19th centuries that the picture became clear. Lavoisier showed that if you capture all the gases released during combustion, the total mass does not change. Nothing was destroyed. The mass of the log just became the mass of carbon dioxide and water vapor and ash and soot scattered into the air. You have to weigh everything, including the invisible gases, to see that the books balance. Energy conservation was even harder to pin down. People had to realize that heat, motion, chemical reactions, electrical currents, gravitational falling, and light were all different faces of the same quantity. That took most of the 19th century and the work of dozens of physicists. Joule did his famous experiment in 1843. using a falling weight to spin a paddle in water and measuring the temperature increase, showing that mechanical energy and heat were interchangeable in exact, predictable amounts. Helmholtz formalized the principle in 1847, and over the next 100 years, every new form of energy that was discovered, from nuclear binding energy to the mass energy equivalents, turned out to obey the same conservation law. We have now tested this law in every domain of physics, in collisions between subatomic particles at speeds near the speed of light, in the interiors of stars, in the radiation from the cosmic microwave background, the afterglow of the Big Bang itself. Never once has the total energy of a closed system been observed to change, not by any amount. The first law is as close to a sure thing as science offers. And there is one more form of energy in your body that I forgot to mention, and I want to add it to the accounting because it is surprisingly large: gravitational potential energy. Right now, you are sitting or standing some distance above the center of the Earth. Gravity is pulling you down. If you were to fall, say from a cliff, your gravitational potential energy would be converted into kinetic energy as you accelerated, and then into heat and sound and deformation when you hit the ground. The higher up you are, the more gravitational potential energy you have relative to the ground. When you are alive, you spend energy constantly fighting gravity. Every time you stand up from a chair, you are converting chemical energy from your muscles into gravitational potential energy. Every time you climb a flight of stairs, you are doing the same thing. Your body is, among many other things, an anti-gravity machine. It takes chemical fuel and uses it to lift 70 kilograms of material against the pull of the Earth. When you die, this fight against gravity also stops. If you are standing, you fall. Your gravitational potential energy converts to kinetic energy on the way down, and then to heat and sound on impact. If you are lying in a bed, the situation is more subtle. Over time, as your tissues decompose, the fluids in your body flow downward under gravity, settling to the lowest points. This is a conversion of gravitational potential energy to kinetic energy to heat, on a very small scale, but it is happening. Even after burial, gravity acts on your remains. Soil settles. The ground above a grave compacts over time. These are conversions of gravitational potential energy into heat through friction between soil particles. Tiny amounts of energy, but real, measurable, and conserved. I want to try something. A thought experiment. The kind of thing physicists do when we want to strip away all the complications and see the principle naked. Imagine a sealed room, perfectly insulated. No energy gets in or out, no matter gets in or out, a perfect closed system. Put a person in that room, alive, with enough food and water and air for a while. The total energy of everything in that room, the person, the air, the food, the walls, the floor, everything is some number. Call it E. The first law says E cannot change because nothing enters or leaves. The person eats the food. Chemical energy moves from the food into the person's body. E stays the same. The person moves around, converting chemical energy into kinetic energy and heat. E stays the same. The person speaks, creating sound waves that bounce around the room. E stays the same. The sound waves hit the walls, and their kinetic energy becomes tiny amounts of heat in the wall material. E stays the same. The person dies, their body cools. The air in the room warms slightly. Bacteria begin their work. Chemical energy becomes heat. Gases are released. Over months, over years, the body decomposes. Through all of this, through every moment from life to death to dust, E has not changed. Not by a single joule, not by 1/1,000,000th of a joule. The total energy in that sealed room at the moment of death is exactly, precisely, to as many decimal places as you care to calculate, the same as it was the moment before death. And it is the same a year later when only bones remain, and it would be the same 1,000 years later, and 10,000, and 1,000,000. That is conservation of energy. It does not care about life or death. It does not distinguish between a living person and a decomposing one. It makes no exceptions for tragedy, for love, for importance. It just says the total stays the same. But I need to tell you about something else now, because it is the part that adds depth to the picture. The second law of thermodynamics. It does not contradict the first law. It sits alongside it and says something the first law does not. The second law says that while the total energy in a closed system stays constant, the quality of that energy, its usefulness, its ability to do organized work, tends to decrease over time. Energy naturally moves from concentrated forms to diffuse forms, from order to disorder, from low entropy to high entropy. Your living body is a spectacularly low entropy system. It is one of the most organized structures in the known universe. Billions of cells, each containing thousands of different kinds of molecules in precise arrangements, all cooperating, all coordinated, all communicating through chemical and electrical signals. You take diffuse, spread-out energy, sunlight scattered across millions of square miles, food scattered across fields, and you concentrate it into this breathtaking, improbable, exquisite structure. And you do this constantly, every second. That is what being alive means, from the standpoint of thermodynamics. Life is a system that fights entropy locally and temporarily by importing low-entropy energy from outside, food and oxygen, and exporting high-entropy energy back out, heat and carbon dioxide and waste. The difference between what comes in and what goes out is what maintains the organization. When you die, that fight stops. The entropy pump shuts down, and the second law, which was always there, always pressing, takes over unopposed. The energy that was concentrated in your body begins to spread. The organized structures break down into simpler, more probable arrangements. Your temperature equalizes with the surroundings. Your exquisitely organized molecules are disassembled into smaller, simpler ones. The total energy has not decreased, not by 1 joule, but the quality of that energy, its concentration, its capacity for doing the kind of sophisticated, coordinated work a living body performs, that quality decreases steadily towards zero. The first law says the energy is conserved. The second law says the organization is not. And that, if you want the physics of it laid bare, is the physical difference between life and death. Life is a local, temporary violation of the second law's tendency, maintained by constant energy throughput. Death is when that throughput ceases and entropy increases toward equilibrium, as it always does, everywhere, eventually. But let me push this one final crucial step further, because I think there is something underneath all of this that most people never hear, and it might be the most important part. I have been talking as if your energy is a thing that belonged to you, as if you were carrying a box of energy around, and at death the box opened and the contents scattered. But that picture is subtly and importantly wrong. The truth is, you were never a fixed thing, not energetically, not materially, not in any physical sense. The atoms in your body right now are not the same atoms that were in your body 10 years ago. Almost every one has been swapped out and replaced. The calcium in your bones was exchanged. The carbon in your muscles was traded for new carbon. The iron in your blood was recycled many times over. You shed atoms constantly, through your breath, your sweat, your skin. You acquire new ones from every meal, every glass of water, every lungful of air. Roughly 98% of the atoms in your body are replaced each year. You are not a thing. You are a pattern, a process. You are a particular way of organizing matter and energy that persists for a while and then stops persisting. Think of a whirlpool in a river. A whirlpool has a shape, it has a location. You can point to it and say, that one there. You can even give it a name, but the water flowing through it is constantly changing. No particular molecule of water belongs to the whirlpool. The whirlpool is not made of any specific water. It is a pattern that the river makes when the current meets a particular rock or a bend in the bank. As long as the conditions are right, the pattern persists. When the conditions change, the whirlpool fades and the water moves on. The river does not lose anything when a whirlpool dissolves. The water was always the river's. You are like that. You are a whirlpool in the flow of atoms and energy through the universe. For 60, 70, 80 years, the universe organizes some of its matter and energy into the pattern that bears your name. Energy flows in as food and oxygen and warmth. Energy flows out as heat and carbon dioxide and motion. You are the pattern in between. You are the process itself, not the material it is made of. And death is the moment the pattern stops being maintained. The whirlpool dissolves. The atoms flow on. The energy continues its journey through new channels. Nothing is lost, because nothing was ever truly contained. You were open. You were flowing. You were the universe doing something interesting with some of its energy for a little while. I want to make sure this point lands, because it is easy to hear it as philosophy and miss that it is hard physics. When I say you are a pattern, I do not mean that in some soft hand-waving way. I mean it in the most quantitative way imaginable. If you could tag every atom in your body today with a tiny label and check back in a year, you would find that almost all of those labeled atoms are gone. They left through your breath, your sweat, your waste, your shed skin cells. New atoms came in through your food, your water, your air. The pattern stayed. The material rotated through. This means something remarkable. You is not a collection of atoms. It is a set of relationships between atoms, a set of rules for how they are arranged and how they interact. When those rules are being enforced by the machinery of your cells, by the code in your DNA, by the constant chemical activity of your metabolism, the pattern persists even as the atoms come and go. When the rules stop being enforced at death, the pattern dissolves, but the atoms and the energy keep going. The energy was never stored in you the way money sits in a vault. It was flowing through you the way water flows through a pipe. While the pipe is intact, the water moves in one end and out the other in an organized, useful way. When the pipe cracks, the water still moves. It just moves differently, less usefully from the pipe's perspective. But the water does not care about the pipe, and energy does not care about you. I do not say this to be harsh. I say it because it is liberating. The energy will be fine. It will always be fine. Conservation guarantees it. The question, it turns out, was never about the energy. The energy was always safe. The real question was about the pattern, and the pattern, while it lasted, was something the universe had never done before in exactly that way and will never do again. There is one more layer, the deepest one, and it is the one I find myself returning to again and again. The energy in your body right now is not new. It was not freshly minted when you were born. It has been around for a very, very long time. Every joule of energy in the universe today was present at the moment the universe began, roughly 14 billion years ago. Energy does not get manufactured. It merely takes new forms. Let me trace your energy backward through time, step by step, because I want you to feel the length of this chain. The warmth in your hand came from a chemical reaction in your cells. That reaction used energy from a molecule that was built from the food you ate this morning. The food got its energy from sunlight that fell on a field last summer. The sunlight was produced by nuclear fusion in the sun's core, where the temperature is 15 million degrees and the pressure is 250 billion times the pressure of Earth's atmosphere. The sun's hydrogen fuel was formed in the first few minutes after the Big Bang, when the universe was a hot, dense soup of elementary particles cooling rapidly, protons and neutrons assembling for the first time. The energy in that primordial hydrogen came from the energy of the Big Bang itself. But even that is not the whole story. Some of the atoms in your body were not made in our sun. The carbon, the oxygen, the nitrogen, the calcium, the iron, these heavier elements were forged in the cores of previous stars, stars that lived and died before our sun was born. Those ancient stars burned through their hydrogen, fused it into helium, then fused helium into carbon, carbon into oxygen, and so on, building heavier and heavier elements, each step releasing energy from nuclear binding. When those stars ran out of fuel, some of them exploded as supernovae, scattering their newly forged atoms into space and releasing more energy in a few seconds than the sun produces in its entire lifetime. The debris from those explosions eventually coalesced into new solar systems, including ours. So, the iron in your blood was made in the core of a star that died. The calcium in your bones was forged in a supernova explosion. The oxygen you are breathing was assembled, atom by atom, through nuclear fusion billions of years ago. You are physically and literally made of stardust, and the energy that put those atoms together, the fusion energy that welded protons and neutrons into carbon and oxygen and iron, that energy is still there, stored in the nuclear binding of those atoms inside your body right now. The energy that is keeping you warm at this moment, that is letting your brain follow these words, is roughly 14 billion years old. It has taken many forms on its journey to you. It has been inside stars. It has traveled across galaxies as light. It has been locked in clouds of hydrogen gas, drifting through interstellar space for millions of years. It has been part of rocky planets, of ancient oceans, of single-celled organisms in a warm sea, of ferns in a carboniferous forest, of the great reptiles, of ice sheets a mile thick, of volcanic eruptions, and now for a few decades it is arranged in the pattern called you. When you die, that energy will continue its journey. It will take new forms. It will end up in soil, in air, in other organisms. Some of it will radiate from the earth as infrared light, and travel through space for billions of years, maybe forever. And in the very, very long run, when the sun expands into a red giant and the Earth is consumed, the energy will still exist, redistributed into whatever the universe becomes next. You borrowed it. For a brief flicker of cosmic time, the universe lent some of its oldest energy to the pattern called you. And for that brief moment, the energy could think. It could wonder. It could look up at the stars and ask where it came from and where it would go. That is what physics says. Not guessing, not hoping, not philosophizing. Careful measurement and the most reliable mathematics human beings have ever developed. The energy is conserved. The atoms are recycled. The pattern is temporary. The substance is eternal. I find that more comforting than any alternative anyone has ever offered me. Not because it promises anything about consciousness or the soul, which are not questions physics is equipped to answer, but because it means the universe wastes nothing. It cannot afford to. The laws will not allow it. Every joule of energy that ever passed through you will be used again. Every atom in your body will end up in something else, doing something else somewhere else. The universe is extraordinarily thrifty. It has to be. The next time you feel the warmth in your hand, take a moment with it. Think about what that warmth actually is. It is captured starlight, energy that has been traveling and transforming for 14 billion years, and it stopped here in you, just for a little while, to do something extraordinary, to be a living thing, to wonder about itself. And when it moves on, as it will do other extraordinary things, different things, in different patterns, in different places, in different times, but it will not stop. It cannot stop. That is perhaps the deepest truth physics has ever uncovered about the nature of reality. The energy goes on. I want to leave you with one thought, something to carry with you after this is over. You are made of energy that has no expiration date. Every part of you was once something else, and every part of you will become something else again. The universe possesses no mechanism for deleting you. It can only rearrange you. So knowing that conservation of energy means you are, in the most literal physical sense, woven permanently into the fabric of everything that was and everything that will be, does that change how you feel about the fact that you are here right now? I am genuinely curious what you think about that.